In this series, I'll present random problems that I encountered during my 9th grade math Olympiad training. I will share my thinking process, tricks and strategies, and if everything goes well, the problems should get more difficult as the series goes on. Enjoy today's problem. Prove that the whole part of the square root of 1 times 2 plus the whole part of the square root of 2 times 3 plus so on till the whole part of square root of n squared plus n is equal to n times n plus 1 divided by 2, where the square brackets represent the whole part and n is a natural number. First, we can factor out n from the last term, thus resulting into the following equation. Now, it's pretty clear to see that each term respects a pattern. 2 is written as 1 plus 1, 3 is written as 2 plus 1, 4 as 3 plus 1, and so on until n plus 1. Each term represents the integral part of a square root obtained by multiplying a number by its successor. Now that we've identified the main pattern of this problem, let's simplify it. We start by examining how the integral part works. The integral to the left of a given number, which is also the largest integral less than or equal to that number, is referred to as the whole or integral part of that number. In this scenario, the whole part corresponds to the position of the green dot on the number line. It's important to note that when the number is an integer, the green dot coincides with the red dot, which is a number, since they are equal. We observe that visually shifting the whole number by adding 1 results into a blue dot that consistently appears to the right of the red dot, never aligning with it. This is because it is always greater than the original number and never coincides with the red dot. The green dot is either aligned with the red dot or to its left, and the blue dot is always on the right side of the red dot. This shows that a real number is consistently greater than or equal to its whole part and less than the next whole number. This property holds significant value and we can utilize it effectively. So let's derive the integral part of each term. There are of course many ways of achieving this, but I prefer naming the integral part of the general term as k. So the whole part of square root of n times n plus 1 is equal to k. Using the earlier property, we know that k is less or equal to the square root of n times n plus 1, which is also less than k plus 1. Squaring this inequality gives k squared is less or equal to n times n plus 1, which is less than k plus 1 squared. And we can write n times n plus 1 as n squared plus n. Now let's focus on n squared less or equal to n squared plus n. We have three cases. If we assume k is less than n, then k squared less or equal to n squared plus n contradicts the assumption, because k squared is less and not equal to n squared plus n, of course. Likewise, if k is greater than n, we can replace k with the smallest integral greater than n, which is n plus 1. However, this leads to the inequality n plus 1 squared less or equal to n squared plus n, and simplifying it shows that n is less or equal to negative 1. Since n is a natural number, this doesn't make any sense. Therefore, since k can be greater or less than n, it implies that k is equal to n. Alright, let's get back to k less or equal than square root of n times n plus 1, which is less than k plus 1, and swap k with n. Using the earlier property, we figure out that The integral part of square root of n times n plus 1 is n itself. Replacing every term from the starting equation gives 1 plus 2 plus so on until n equal to n times n plus 1 divided by 2. This holds true thanks to Gauss' formula.